In this video lecture, I have determined the value of magnetic susceptibility by an experiment that is basically related to the Quink's method. So the measurement of magnetic susceptibility and the mass susceptibility is performed here, and some are the basic points which one miss into this particular experiment. This experiment is performed in generally engineering physics labs, where one measure the magnetic field density and put that value in the calculation and perform the experiment. But I have shown here systematic that the magnetic field density is not important. Here the magnetic field intensity is important, and how one can take that magnetic field intensity by the magnetic field density. Second point is that related to the formula, that which formula is important basically for the measurement of magnetic susceptibility, right? And the third point is related to the graph. One have to take the mean of the observation, or one have to take the graph, which is best or a concept for the calculation and ultimately the measurement of this experiment. So what precautions basically one have to keep to make the graph, that is shown here. So let us see the calculation for the magnetic susceptibility and what are the important points here. In this video lecture, I will discuss the calculation of Quink's experiment by which one can find out the magnetic susceptibility or mass susceptibility. So the aim of the experiment is to measure the magnetic susceptibility of FeCl3 solution by using the Quink's method. So this is the aim of the experiment, and you have seen experiment in this way, where these are two coils in which DC current flows, and as a result the steel rod inside the coil at the center of it becomes as north pole and south pole. So these are known as electromagnet, right? So this is the U-tube in which FeCl3 solution is filled. So the second arm of this tube is kept inside the electromagnet in between these two poles. So magnetic field lines are shown from north to south. This is the direction of the magnetic field. So this is a block diagram of the experiment, and before we put this Quink tube in between these two poles, we calibrate the magnetic field intensity of these two poles, right? So now we check the intensity of magnetic field by giving some current to these coils, and then as a result the magnetic field intensity. But here I have noticed some point in this experiment. Generally the people which perform it, they measure magnetic field in terms of kilogauss or in the unit of Tesla. It means they measure the magnetic field induction, right? So this is one of the important point in the calculation of this particular experiment. The observation which is taken in this way: serial number, current is in ampere, fall in height, that is in m, or raise of the level. I have written here fall in height because in my experiment I have keep this section in between these two poles. This is a little bit contradiction with any other person, but it does not matter for this calculation. If I will keep this arm in between these two poles, so level of this solution, basically level will rise up here, and that will fall on the other side. So it means I have noticed the observation on the second hour, right? That is in terms of the unit of meter. Then magnetic field is measured in Tesla, so that is by different current. And then after I have converted this magnetic field density, magnetic field induction in terms of the magnetic field intensity H, and that unit is ampere per meter. So the point is that maximum I have seen people note this magnetic field density, and on its basis they perform the experiment. But if we have to perform, or we have to observe, calculate the measure the magnetic susceptibility, for that H will be required, and that is the magnetic field intensity. For that, the magnetic field intensity is written as B is equal to mu naught H, right? Because from the experiment we measure the magnetic field density in terms of kilogauss. Then after we change that value in Tesla, because 1 Tesla is equal to 10 raised power 4 Gauss. 1 Tesla is equal to 10 raised power 4 Gauss. We measure generally this point, this B, and that is the magnetic field density or magnetic field induction. But in our calculation, our requirement is of the H. So H one can get by this formula, B is equal to mu naught H. So I have used here this H by using this formula. So H is equal to B upon mu naught. This is the point of this calculation especially. So B is equal to mu naught H. So at the first reading, the current was 1 ampere. Fall in height, there is no change at 1 ampere current, but the density of the magnetic field was 0.373. This is in terms of Tesla, and I have converted this magnetic field density in the magnetic field intensity, and that in terms of H, ampere, that unit is ampere per meter, is equal to 0.029697 into 10 raised power 7. So in my calculation, this is the only difference. I have considered here the magnetic field intensity for each value of the current. So at 2 ampere I have noticed that change in height, that was 1 into 10 raised power minus 3 meter, correspond field density, and as a result of magnetic field intensity. At third time, for serial number 3, the third set of the reading, when the current supplied to the coils. So here you can see these are coils. These coils are attached with the power supply, and from there we provide we provide current to these coils, and as a result magnetic field intensity change here. So with serial number 4, the current was 4 ampere, and then change in height was 3 into 10 raised power minus 3 meter. So the height basically changed into millimeter. I have converted all those scale basically into SI system. So I am writing meter here. So 3 into 10 raised power minus 3 meter. This is in Tesla, 1.08 Tesla, and this is in again intensity in terms of ampere per meter, that is H. So corresponding to each current at set number 5, this is the change into height, this is the magnetic field density, and this one is the magnetic field intensity. So in the calculation of magnetic susceptibility, we have to basically focus on this point also. We have to measure the susceptibility, and for that H is required. And in our calculation or in our observation, what we do, we just observe the density B and we put direct that value in the formula. So here one have to note down that this B have to change in terms of H. So we have to use actually H. So H will come through this formula, B is equal to mu naught H. So H A R this value. And now for the these values of change in height and this H, we have to take plot. Fall in height is represented by H, and this is capital H. Capital H is the magnetic field intensity, small h change in height. This unit of H is in meter and the unit of capital H is ampere per meter. So I have to make a graph between small h and capital H square. So for that I have to take square of all these values. That graph basically is made by this way. On the x-axis I have put all these values, H square multiply by 10 raised power 7 ampere per meter whole square. It means I have used here square of the term, right? So on x-axis I have considered the magnetic field intensity in terms of H square and the unit of that. On y-axis I have considered the fall in height, that is H, in terms of unit of meter, that is into 10 raised power minus 3 meter. This factor 1 2 3 4 5 6 up to this. So 1 means 1 into 10 raised power minus 3 meter, 2 means 2 into 10 raised power minus 3 meter, and on the x-axis this 0.004 into 10 raised power 7 ampere per meter and is whole square of it. That means 10 raised power 14 ampere square meter square. Similarly for this 0.006 into 10 raised power 14 ampere square meter square. So this is the point. So now for this particular slide, now where I have made the graph of the calculation which I made earlier of this particular observation. So what is the important point before you make a graph? So I want to mention some point here, that before you draw the graph on your sheet, graph sheet, it's first of all make the scaling proper. So how to make scale? So scaling is important before you draw the any point on the graph paper. I have made this graph paper by a software. So for that scaling, what is important on x-axis, what parameter basically you have considered and what is the scale of that. So here on x-axis I have considered 0.002, that is basically H square in terms of the this particular factor, which is square of the 10 raised power 7 ampere per meter, right? So here this x-axis, along x-axis I have considered H square, and 0.002 is equal to 1 box. In graph paper 1 box is equal to 10 small division, right? On y-axis what I have considered, on y-axis I have considered that 1 of H, this 1 division from this 1 is equal to 1 box. 1 box in graph paper is equal to the 10 small division. Right. So first of all these points are important before you make any graph related to any observation, so first of all you have to make a scale, that what you are considering on the x-axis and what you have considered on y-axis, and what the interval you are taking, and how much basically that is comparable on the graph paper. So as I have written here that my 0.002 multiply by this factor is equal to one box of the graph paper, and on the one box is equal to 10 small division on the graph paper. And similarly for y-axis, 1 I have considered height, that is 1 interval of 1 is equal to one box, and that is equal to the 10 small division on the graph paper. Here I have mentioned here already that h square is what? This is 0.002 into 10 to the power 14 ampere square upon meter square. H is equal to 1 into 10 to the power minus 3 meter. So these are some points which we have to keep in our mind to make a graph paper for any calculation. So after this scaling, what I have what is the most important point? See, these are original data, this one, this and this. All these 5 points basically are taken from the observation table, and these, if I connect all these points, the behavior is like this one. But I have to take slope of this graph paper from this line. So what I have to do for that purpose? If I will take the slope between this point and this point, that will be different from this point, and if I raise here this point, because these are not parallel line, right? Similarly these are not parallel line, so the slope will be different. So for such type of situation, what we have to do? So for this we basically join all those points by a line which passes nearby to the other points. Like I have joined all these points. This is not connected to this line, but this line passes through this one, and similarly this line passes near about to it, but it is so far. But on the next end here, this is connected to the point. So when I join initial and end point, I found that this line passes almost near to all the points. So I will take the slope from this line. So I have considered a point here, that is on this particular line, right? And see, this is the next point. So slope is equal to AB upon BC. So what I did, I just select a point on x-axis, this one, it cuts here, and the next point along the x-axis is this one, which cuts this line at this point, C, and similarly I choose these 2 points, any 2 points. Or you can say that I have selected this point, I take a perpendicular on this axis and on this axis, then next point I choose this one, I take the perpendicular and it cut this axis here and y-axis at this point. Now I join these lines, so I found a triangle, this ABC. So slope is defined by this AB upon BC. So AB, this A point is basically defined through x2 y2, and this C point is defined by x1 y1, right? So y1, this is x1, this is x2, this is y1, and this one is y2. So the coordinate of this point will be x1 y1, and for this point that will be x2 y2, and as a result when I will found the slope, that will be defined by this way. So slope is equal to AB upon BC, and that is equal to delta y upon delta x. The difference between delta y is y2 minus y1, and delta x is equal to x2 minus x1. So when I found this value, the slope basically, which is defined by this way, h upon h square. When I take the slope of this line, what will be that? What is on y-axis? That is h. What is on x-axis? That is h square. So slope will be equal to h upon capital H square, and the result of it will be in this way. You can calculate it from the points. So now slope is equal to h upon h square, and the value of that is 1.1 into 10 raised power minus 3 meter upon 0.002 into 10 raised power 14 ampere per meter square. So from the observation table, this was the observation table. Here I have observed some point in the experiment, that was the current. I was changing the current, so because that is variable. Height was changing of the level, that is also a variable. And as a result of current variation into the current, magnetic field density is also changing, so this is also a variable. So ampere current, height, and the magnetic field density and intensity, these are variables. So I have considered here the slope between h and h square. This is h square. So I have considered these 2 points, 2 variables, and find out the slope of that by this way. So in this part I just told about that how to make a graph, right? So first of all, that you have to make a scale, and then after take the slope. It is not necessary that always your data, your observation points fall on a straight line. Then for the straight line, how to draw a straight line in the graph by using these data points. So that line basically passes nearby to the maximum points, and here you can see that I have only 5 points. So all these points, 3 and 4 points, are near about to the line or at the line. Only 1 point is far away from it, so I can consider this line. This is the logic of this particular concept. So when you observe that all the points, data points, are not coming on the line, so you just draw that line. You just draw a line which basically passes near about to all the points. So it does not matter if my point fall here or there, but maximum point should lie near or at the line which you are drawing yourself. So by this way you will basically take the average of those points. I have noticed one more important point, that instead of making graph, one can take the mean also. So when you take the mean, I don't find that that result is comparable to the slope. From slope also you are taking or you are considering the same thing, but result might be different, right? So it is better that you instead of taking the mean of those value, you just make a graph, and from the graph you find out the slope, instead of finding out the mean of all these value and mean of the height. Mean that is the different point of discussion, but the right thing is here, when you make the graph, then that time you have to focus on this point also. If all the points are not falling on the line in a straight line, then you just draw a line, right, which passes near about to the other points. So now for my calculation, I will consider this slope which I have calculated by this way, and slope is calculated on the other page by this way. And formula for magnetic susceptibility is this one, chi is equal to 4h rho g upon mu naught h square. Here I have considered h and h square separately by this way. This is slope, right, which I have calculated into the earlier slide by using a graph paper. Now the question is that why I am using this formula for the magnetic susceptibility. In general, there is no mu naught or for this number in some formulas, which I have also seen in some manual, but this formula is derived by using a proper concept that I have discussed in earlier slide. You can see here that in this particular experiment, the level of this liquid rise up because of some forces, and that some force basically is calculated on the magnetic dipole, right? And from that we have derived this formula. It is not necessary to discuss all these things here again and again. It is mentioned in an earlier video lecture. So this is already derived formula by this way: 4 mu naught h rho g upon b square. B you can write as mu naught square, h square, mu naught cancel out, so you will get here mu naught h square. So I have derived already this formula, so it is not necessary that we discuss it again. So if one want more information about this formula, you can see that video. But now the point is, for the magnetic susceptibility formula, that is for h rho g mu naught h square, where h is considered fall in height, g is acceleration due to gravity, unit is meter per second square. I have considered all the variables parameter here in SI unit system. So fall in height in meter, g is meter per second square, rho density of the solution, FeCl3 solution I have used here in our experiment, ferric chloride, and the density of that is defined in the unit kilogram per cube meter, and H is the magnetic field intensity, that is in unit of ampere per meter, and mu naught is the permeability of free space, that is 4 pi into 10 to the power minus 7 Newton per ampere square. Right, this is the formula, and now I am putting the value of which I have taken from the graph, and so the magnetic susceptibility formula is this: chi is equal to 4h rho g upon mu naught h square. Solution use FeCl3. Density of this solution is 2.9 into 10 to the power minus 3 kilogram upon 1 into 10 to the power minus 6 cube meter, or you can write it 2.9 into 10 to the power 3 kilogram per cube meter. So this is the density of the FeCl3 solution in this experiment. Slope I have calculated from the graph, that is h upon h square. Value of that is this one. G, value of G, acceleration due to gravity, is 9.8 meter per second square. Mu naught is permeability of free space, that is 4 pi into 10 to the power minus 7 Newton per ampere square. So chi, the magnetic susceptibility, is equal to 4 rho g upon mu naught into h upon h square. As I have already mentioned that this is the slope. I will put this value from the graph. And now the calculation. This chi is equal to 4 rho g upon mu naught, that is into slope. This was the formula in earlier slide. Value of rho, that is 2.9 into 10 to the power minus 3 kilogram upon 1 into 10 to the power minus 6 cube meter. Value of G, 9.8 meter per second square. Value of mu naught is 4 into 3.14 into 10 to the power minus 7 Newton per ampere square. and value of the slope from graph is 1.1 into 10 to the power minus 3 meter upon 0.002 into 10 to the power 14 ampere per meter whole square. Right, now the simplification of this calculation chi, that becomes 125.048 into 10 to the power minus 6 divided by 0.02512 into 10 to the power 1, and these are the unit: kilogram meter per second square, kilogram meter per second square into meter, meter cube Newton per ampere square, and ampere square meter square, ampere square meter square. So these are the values, unit. So now you know that kilogram meter per second square is what? That is force, and unit of that will be Newton. So Newton cancel out. Here ampere square cancel out. This is meter cube and this is meter square, so 1 meter square cancel out, meter by this way. So now you find that there is no unit in this calculation. So chi you will get only this 497.80 into 10 to the power minus 6, and without any unit. This is called magnetic susceptibility of FeCl3 solution, right? And if you want to find out the magnetic mass susceptibility, then you have to divide it by rho. So chi is equal to 4g upon mu naught and slope. There is no value of rho, as you have seen here, right? So there is 4 rho g upon mu naught into slope. This is called magnetic susceptibility in general way. There is no unit of magnetic susceptibility. You have seen into this way also, chi is equal to m upon h, where this chi is the ratio of two intensity. One is the intensity of magnetization of the substance, that how much that magnetic material is magnetized, and h is the intensity of the external magnetic field, right? So there is no unit of chi. And similarly here in our calculation we found that there is no unit of this chi, and that is very small, that is positive but near to 0, right? So the chi is positive near about to 0, and that have no unit. So in case of mass susceptibility, if you want to calculate mass susceptibility, that chi will be equal to again near about to 0, greater than 0 here, into 0.1716 into 10 to the power minus 6 cube meter per kilogram. So this is the mass susceptibility. So in Quincke's experiment by which we measure the magnetic susceptibility, I have considered in this calculation that one have to basically use magnetic intensity instead of using the magnetic field density in the observation table. So in general we use Gauss meter to measure the magnetic field density. In that particular experiment, the apparatus which one use basically, that is Gauss meter, and the range of that remains 2 kilogauss to 20 kilogauss. That means if the unit is in terms of Gauss, it means you are just measuring the magnetic field density, not intensity of the magnetic field, right? So I have just modified this observation table here, and using this magnetic field intensity, and by using I found that there is no any problem inside the calculation or anywhere, right, in terms of the unit or other point. So by this way one can calculate the observation for the magnetic susceptibility or mass susceptibility by using the Quincke's method. So this was the way of calculation in this particular experiment. If you found any problem or you have any problem related to any concept, you can message me, or you can write some comment below this video. Thank you for watching this particular video. And In this calculation of magnetic susceptibility, I have considered here magnetic field intensity instead of magnetic field density. But in this experiment, basically what we do, we just measure the magnetic field density by using the Gauss probe, right, in terms of kilogauss, and then after we change that if we use SI system in Tesla. But this is not the right point. We have to take magnetic field intensity, that is H, and that you take from the Gauss meter, because the formula for H is equal to B upon mu naught. You just measure the magnetic field density B and divide that by mu naught, then you will get the magnetic field intensity H, which is required in this particular experiment where you measure the magnetic susceptibility. Second thing is the graph. Instead of taking the mean of all these values which you have made in your observation table, you should make the graph. And in that graph, basically it is not necessary that all the points fall on a straight line. It might be that some points remain away from the straight line. It might be, but when you take the slope, so slope you take from a straight line portion. So you just draw a straight line from the original point as I have made there, and join it up to the last point, and see that maximum points lies on it or remain near to it. So you have to make such line when the points basically are not fall on a straight line. So this is the second important point which I have considered. And third and most important point, that I have derived the formula by using the force on magnetic dipole, which basically exists inside the FeCl3 solution, by using a reference research paper. So that formula is totally different from the manual which we consider here in India, and this formula basically provide the exact magnetic susceptibility, and proper use of variables I have used here, right. So by this way one can measure the magnetic susceptibility. If you have any problem related to any point or any observation, you can message me below this video. Thanks for watching.